continuing on here with section 2, this Laplace transformation stuff, we're going to jump into another example here. So for this one, determine again the Laplace transform of the following. So this one's going to be a little more complicated. In fact, I don't even know how to do this. Let's see. Here we go. We did it. So this is going to be a function here, f of t, that we're going to break down into 3 different parts. It's going to be the function 2 whenever 0 is less than t is less than 5. It's going to be the function 0. This is whenever 5 is less than t is less than 10. And it's going to be the function e to the four t. I couldn't read my handwriting there. E to the 4t, and this is going to be whenever 10 is less than t. Okay. Cool. So for these piecewise functions, the Laplace transformation actually turns out to be very nice, and it works out really well. So let's just jump into it. Remember that there's a definition here for this Laplace transformation. We can label it either capital F of S, or it could be that cursive L of the function, curly brackets of the function f of t. But just the straight definition is that this is just the integral from 0 to infinity, where we multiply e to the negative st onto the function dt. Okay. So for our example, when we do this this integral, when we integrate over the function f of t, as my t ranges from 0 to infinity, from 0 to 5, I'm integrating just over the function 2. From 5 to 10, I'm integrating over 0. And then from 10 to infinity, I'm going to be integrating f of t to be the function e to the 4t. So we can break this up into the 3 different integrals, and then using the addition rule for integrals to work it all out. So my first integral is just going to be going from 0 to 5. It's going to be that e to the negative st out in front, and then my little f is just going to be 2. All right, and we're going to add on to that another integral. This integral going from 5 to 10 of e to the negative st. Oops. But this time multiplied, my function f is just going to be the value 0 at this part, dt. So that will go away. And then one more. This will be the integral from 10 to infinity the rest of the way. The e to the negative st. And now my function f of t is e to the 4t dt. Okay, and so we can do these without too much issues here. I'd probably factor a 2 out of this first integral, and then we can just do the antiderivative. This middle integral, of course, is just going to be 0. And then this last integral, we're going to do that same trick that we've seen in the past. So let's write it all out. We're going to take the 2 out of the first one. It's going to be 2 times the integral from 0 to 5, e to the negative st dt, plus the middle integral is gone. The last integral, the integral from 10 to infinity, and then we're going to rewrite these e's by multiplying them together and combining the exponent to be e to the negative s minus 4 of t. Remember we did something like this in a couple of examples ago in the first video. Okay, antiderivatives now. So this 2 is coming out, and then the antiderivative here is that we're going to bring down a negative 1 over s, and then leave the negative e to the negative st alone. That's going to be ranging from 0 to 5. Oh, I didn't put my little special thing. From 0 to 5. Oh, it worked out anyway. Okay, cool. Now I know I can do that. Plus, the antiderivative for this other one over here, we're going to be bringing down that negative s minus 4 into the denominator, so negative 1 over, we have to be a little bit careful here, s minus 4, okay? And then leaving it alone. And then that is going to be ranging from 10 to infinity. It worked out there too. That's so cool. Okay, great. Okay, now we can just do it. So if I plug 5, remember you're plugging 5 into the t values since we integrated with respect to t. This is going to be our final answer here. So if I plug the 5 in, we're going to get negative 2e to the negative 5s. That's all divided by s. If I plug 0 in, the e term just goes away, and it's a double negative, so it's going to be plus 2 over s. Over here, if I plug infinity into this, I'm just going to get 0. So minus, plugging 10 in for the t value, we're going to get e to the negative 10 times s minus 4, all divided by that s minus 4. Okay, and then just one more thing. Remember that you also have to determine for which values of s is your function going to exist. So for us, this is going to exist as long as my s value is greater than 4. But notice that what we have here, right, is that we started with this this function that's all broken up, this piecewise function, and when we do the Laplace transformation, we end up with a continuous function that exists after 4. Okay, so it works really well for some complicated looking functions, and you'll see why this Laplace transformation is very important here once we start getting back into differential equation stuff. There's still a few more things that we need to talk about here, so a theorem. Now that we have a Laplace transformation, we do need to talk about the properties of that. One property of that is the linearity of the transform. So let there be 3 different functions here, f, f1, and f2. Whoop, we lost them. There they are. So let there be these 3 different functions whose Laplace transforms exist. Exist. As long as we have that the s is greater than some value a for whatever that needs to be, then there's 2 different things that we can say here. The first thing that we can say, let's get our little symbol here, that the Laplace transformation of f1 plus f2, so if you ever have 2 functions that are added together inside the Laplace transformation, that's the same thing as just taking the Laplace transformation of the first function plus the Laplace transformation of the second function. Okay, so that's very nice about this is instead of doing the Laplace transformation and then adding together, we could just add the functions together and take the Laplace transformation, whichever way is easier based on the problem. One other property that we get that's really nice is that if you have the Laplace transformation of some constant times a function, that's the same thing as just taking the constant out. So you can pull a constant out of these Laplace transformations, and it works out just fine. All right, so the Laplace transformation of a constant times a function is the same thing as that constant times the Laplace transformation of the function. This allows us to do some pretty cool things, so just a couple of examples. The first, I guess we'll just do one quick example here. Let's say that the example is asking us to do the Laplace transformation of this function, 11 plus 5e to the 4t minus 6 sine of 2t. So this example is chosen for a reason because we've done all of these individually before, but now they have constants that's multiplied out in front, and of course they're all added together. So this first thing is really just a constant function, and we've seen the Laplace transformation of a constant function. We only did it with the value 1. So now we're going to pull that 11 out as a constant, and now we're taking the Laplace of 1, and Laplace of 1 was 1 over s. We did that in the first video. Plus this one. So we have that constant of 5, which we're going to pull out, and then it's just the Laplace transformation of e to the 4t, and we've seen that one before as well. You may need to go back in your notes or go back to that video. This was 1 divided by s minus, s minus 4. Okay, so that's the Laplace transformation of e to the 4t. That is going to be minus 6 for the constant here, and we did sine of 2t in the past. So again, just looking it up from before, sine of 2t was 2 divided by s squared plus 4. Okay, so and it's just as easy as that, like we're done. Just taking the constants out and then using the Laplace transformations of stuff that we've already done in the past. In fact, you are very rarely going to ever have to actually do the integration to find the Laplace transformation. So just scrolling up here, this example that we did, you are not going to have to actually do the definition for the Laplace transformation all that often. What you're going to have to do is to go to the book. So here's the book. This is page 356. and they just have a table with a lot of very common Laplace transformations. So here you see the constant 1. The Laplace transformation of that is 1 over s. E to a constant t is 1 over s minus that constant a. And then they just have a bunch of different other ones. So if you ever are having to do a Laplace transformation for any of these common functions, we already have a transformation here with the restriction. And then keep in mind, right, just like we saw in this example, is that if you also have a combination of very common ones with constants in front, we can use this linearity theorem to make it very nice for us. Okay. Great. So let's do one last example here before we jump into the next video. Just more practice of doing something like this. So what we're going to do here is a Laplace transformation of the function 5t squared e to the negative 3t minus e to the 12t cosine of 8t. Okay, so let's just go term by term. Let's worry about this first one. First off, there's this 5 out in front, and we can take that 5 out of the Laplace transformation. Then we have this t squared e to the negative 3t. So let's go to that table in the book and see if we can find anything that looks familiar to a t out in front that has an exponent, and then an e with a constant times t. And just doing that, it looks like it's this one here. So that's going to be t. My n is 2. So it's a t squared, and then we have an e, I think it was what, negative 3t? Yes, negative 3t here. So my a is going to be negative 3. So just replacing my n's with 2's and my a here with negative 3, we're going to end up with this. I already have it in my notes, but I hope you have the book in front of you that you can just kind of see what it is on both sides. Oh, you know what I could do? Let's do this. Am I going to be able to get it over there? Of course not. We're not that lucky. Let's see if I can do it like this. There we go. That works out. All right, so we have this 5t squared e to the negative 3t here. So the 5 we pulled out. We have an n factorial. Remember, the n factorial was 2. 2 factorial is just 2 times 1, which is 2. And we're going to divide that by s minus a. Remember, our a is negative 3, so that's really going to be s plus 3. And that is going to be raised to the n plus 1 power. If n is 2, then 2 plus 1 is 3. We are raising that to the 3rd power. So this is the Laplace transform of t squared e to the negative 3t. All right, that's going to be minus. So the negative 1 we're kind of pulling out of the Laplace transformation. Then we have this e to the 12t cosine 8t, and that looks like this bottom one down here, where my a is 12 and my b is 8. So just plugging that into here. So we already took the minus sign out. Then it's going to be s minus a, so s minus 12 up top. That divided by the denominator here, s minus the 12 squared plus the b, which is 8 squared, which is 64. Cool. And that's it. So that's all there is to it. There's one last little thing that we do need to worry about. And don't forget, anytime you do the Laplace transformation, you always have to worry about the restrictions of your s. You can either just look here or look over here. So that first thing that we did, our s has to be greater than this value of a, where this value of a was negative 3. So in other words, 0 to infinity. But this one down here had to do for this value of a, where this value of a was 12. So combining those two things together, this has to be bigger than 12 for this to exist. Okay, great. So pausing the video here. I'm going to pick it up in the third video.